Greetings and welcome to the video introduction to problem set number 6 of Chemistry 221. And in this problem set video, we're going to look at both chapter 6 and chapter 7, part 1, which is essentially section 7.1 to 7.2. You do not have to look past section 7.2 for this particular section. So like the other videos, when you've talked about it, doing your problem set, make sure you show your work, make sure you use my periodic table, mhchem.org/per-tab. And again, you can watch this video as much or as little as you need to make the corrections. But I do want you to correct your work, okay? So on every problem, both the problems which are right and the problems which are not right, I want you to put some kind of a mark. So next to the problems that are right, put some kind of self-correct symbol so that I know that you know that the problem's right. And the problems that you didn't get right, which by the way is totally cool, make some notes on how to do it right, like how the correct answer should have been found. And that's all there is to it. It should be pretty chill, but I do want to see your work all over the problem set. If you turn in a perfect problem set but no self-correct marks, you will not get full credit for this assignment. On the other hand, you can miss like every problem on the problem set, but if you self-correct, show how you would do things differently next time, stuff like that, full credit. So it's very important to me. And if you get stuck on any of this material, please reach out to me. You can also talk to the AVID/LSC Center located above the MHCC library on the main MHCC campus. It should be pretty chill. And you'll turn this in corrected at the beginning of your lab period on the due date. For this problem set, you will need the solubility table, which is a handout. You can get it at mhchem.org/SOL. And it will be helpful as you need to determine which compounds are soluble, i.e. you write AQ next to, and which compounds are insoluble, i.e. which ones you write S next to for the states of matter. It'll be pretty important. So if you can have this next to you as well as the periodic table, you should be good to go. Okay, let's get into this problem set. Iron 3 oxide, Fe2O3. We want to find the weight percent of iron in iron 3 oxide. And then also we want to know how much iron is present in 25 grams of Fe2O3. Okay, weight percents in chemistry are usually not too bad. In a weight percent, what I recommend doing is first you find the molar mass of what you're looking for. So find the molar mass of Fe2O3. Whatever that is, that's going to go in the bottom, in the denominator. And in the top part, you want to put just the grams of what you're looking for. So because we're looking for iron, we would put 2 times 55.85. 55.85 is the molar mass of one iron. We have 2 of them, so you'd go 2 times that number. So the weight percent, again, pretty chill. First thing you want to do, find the molar mass. So 2 irons and 3 oxygens, 159.70 grams per mole is the molar mass. And then weight percent will be grams of iron in the top divided by grams of everything in the bottom times 100%. The grams of everything in the bottom number is 159.70. And the grams of just iron, you would go 2 times 55.85, the number on the periodic table. So 2 times 55.85, the iron in iron 3 oxide, divided by 159.70, the mass of everything times 100%, 69.944%. Pretty large number. I'm calling it 5 sig figs because 2 times 55.85, where 2 is absolute, would give you a number that's larger. And then you're dividing it by 5. But whatever. If you use 69.94, that's fine. If you get around 69.9, I'm very happy. All right, it doesn't really say. For the next part of the problem, we have 25 grams of iron 3 oxide, and we want to know how many grams of just iron we have. And that's where these weight percents are cool, because what that number means is that in 100 grams of Fe2O3, you would have 69.944 grams of just iron. And that's kind of like a relationship. You can use that as a conversion factor, because in the next part of the problem, you have 25 grams Fe2O3. In 100 grams of Fe2O3, you have 69.944 grams of iron. That's again straight from this percentage. Multiply these two together, 17.5 25 grams of iron can be found in 25.0 grams of iron 3 oxide. But the important part, once again, molar mass on the bottom, amount of what you're looking for on the top times 100%, that's going to allow you to find the mass percent or weight percent of the element in the compound. An organic compound has the empirical formula C2H4NO. If the molar mass is 116.1 grams per mole, what is the molecular formula of the compound? This question is a way to go from an empirical formula to the molecular formula. And to go from the EF to whatever the molecular formula is, you need two things. You need the molar mass of the whole compound, which is something that has to be given to you, that you're not supposed to know it. You also need the molar mass of the empirical formula. So in a little bit here, we're going to add up 2 carbons, 4 hydrogens, 1 nitrogen, and 1 oxygen. And whatever that number is, we're going to compare it to the 116.1 number. And it's going to be a ratio that's a whole number. If you put the bigger number on the top and the smaller number on the bottom, you're going to get numbers like 1 or 2 or 3. You won't get 1.5 or anything like that. So let's see what this comes out to be. The empirical formula, molar mass of the empirical formula is 58.06. And again, that number came from 2 carbons plus 4 hydrogens plus 1 nitrogen plus 1 oxygen. 58.06 grams per mole. That's the empirical formula's molar mass. And the next thing we're going to do, big number on the top, small number on the bottom. So 116.1 divided by 58.06, that ratio will be a whole number. You'll never have fractions. And that's pretty gosh darn awful close to a ratio of 2. And that 2 is important. That tells you how many empirical formulas are in your molecular formula. So the molecular formula of this thing is going to be 2 empirical formula units. So we're going to take C2H4NO twice. Molecular formula C4H8N2O2. So again, find the empirical formula's molar mass. 2 carbons, 4 hydrogens, a nitrogen, and oxygen. You'll compare that number to the molar mass of the whole thing. Bigger number on the top, smaller number on the bottom. You're always going to get a whole number, and that whole number is what you multiply the empirical formula by to get the molecular formula. If the ratio would have been 1, then the empirical formula would have been the molecular formula as well, and that does happen for things like water. But in this case, we multiplied the empirical formula by 2 to get the molecular formula. And if you put a star next to this one's really important, because what we're going to do on this problem is take lots of the previous problems and put them all together. And the ultimate goal here is to find the molecular formula for this compound. And this compound has carbon, oxygen, and fluorine in those mass percents. And it also says that the molar mass of the whole thing, 82 grams per mole. So let's use our skills from the previous problem and knock this thing out. And what we're going to do is we're first going to turn those 3 percentages into grams. We'll assume 100 grams total. We'll then go grams of each of them to moles. We'll compare the moles to each other, smaller on the bottom, bigger one on the top. That's going to lead us to the empirical formula. And the empirical formula's molar mass will be compared to 82 grams per mole. And using that ratio, we'll be able to find the molecular formula for the compound. Okay, no problem. Let's do it. So again, take the percentages, turn them into grams, and go grams to moles. All right? If you assume 100 grams, it makes your world a lot easier because you don't have to think, but you can use any number you want to. But if you're like me and you're lazy, let's be honest, then just assume 100 grams, 14.6 grams of carbon, 39.0 grams of oxygen, 46.3 grams of fluorine. And you've got to turn them into moles. So the numbers there are just the molar masses of CO and F. And you end up with 1.22 moles of carbon, 2.44 moles of oxygen, and 2.44 moles of fluorine. This is, like we talked about earlier, a very rough formula. You could write C 1.22, O 2.44, F 2.44, but that's a really ugly formula. So to clean it up and make them whole numbers, divide all of those numbers by the smallest number, which is 1.22. 1.22 divided by itself is 1. 2.44 divided by 1.22 is 2. So you have 1 C, 2 O's, 2 F's, empirical formula CO2F2. That's the empirical smallest whole number ratio of atoms. You're good to go. So this is the first step, but to get to the molecular formula now, we're going to use the empirical formula. We're going to calculate its molar mass, and we're going to compare it to the piece of information we haven't used yet, which is the molar mass of the whole compound. Knowing that the empirical formula is CO2F2, let's find the molar mass of the CO2F2 empirical formula. And again, we'll do this like we've done it before. 1 carbon would be 12.01 grams per mole. 2 oxygens, 2 times 16, 32, 2 fluorines, etc. Add those up, 82.01 grams per mole. This is the empirical formula's molar mass. And we want to compare that to the molar mass of the whole compound, which you can see is also 82 grams per mole. So 82 divided by 82 is just 1. That means in this problem, the molecular formula equals the empirical formula, or CO2F2 taken once, CO2F2. So CO2F2 is both the empirical formula and the molecular formula, and that does happen. So like H2O has an empirical and molecular formula which are the same. You can't reduce H2O down to smaller whole numbers. On the other hand, H2O2, hydrogen peroxide, has an empirical formula of just HO. So that one has a different empirical and molecular formula. But CO2F2 is like H2O. The empirical and the molecular formula are the same. We're going to change gears now here a little bit. We're going to talk about molarity. And this question says, what's the mass of solute in grams in 125 milliliters of a 1.023 times 10 to the minus 3 molar solution of sodium phosphate? And then it also says, what's the molar concentrations of the sodium ion and the phosphate ion? So big M right there is going to be something we're going to use a lot from here on in. Big M stands for moles per liter, and it's moles of solute over liters of solution. So in this case, that means moles of sodium phosphate per liter of solution. Now we have 125 milliliters. We need to turn that into liters, and you're going to use this transformation a lot. There's 1,000 milliliters in a liter. So 125 divided by 1,000 would give you the volume in liters, and you'll multiply that by the moles per liter, the molarity, the big M. Liters times moles per liter is going to give you moles. That's going to be moles of sodium phosphate. And like the things we've done before then, you can go from moles to grams by using the molar mass of sodium nitrate. So let's sum this all up. Molarity, big M, moles of solute per liter of solution. In the first part of this problem, we're going to take the volume in liters. So 125 milliliters is 0.125 liters. We're going to multiply it by the molarity, which is this part right here. It's a lot of letters, but that's what it is. 1.023 times 10 to the minus 3. The liters cancel out, and you've got moles. And then this number right here, this is the molar mass of sodium phosphate. So you add up 3 sodiums plus a phosphorus plus 4 oxygens, and you get that 163.9 number. In your calculator, 0.125 times 1.023 times 10 to the minus 3 times 163.9, 0.0210 grams sodium phosphate. So if you wished to make 125 milliliters of 1.023 times 10 to the minus 3 molar solution, sodium phosphate, you would measure out 0.0210 grams sodium phosphate, place it in 125 milliliters, shake and stir. That's going to be your 1.023 times 10 to the minus 3 molar sodium phosphate solution. Okay. Now, the second part is important though. The formula for sodium phosphate, you can see there are 3 sodiums and 1 phosphate. So 1 mole of sodium phosphate will have 1 mole of just phosphate. But 1 mole of sodium phosphate, it's going to have 3 moles of sodium. So when it says something about the molar concentrations of sodium and phosphate, the phosphate's going to be easy. The phosphate and sodium phosphate 1 to 1. So the phosphate concentration 1.023 times 10 to the minus 3. Here's the equation itself. Sodium phosphate and phosphate are 1 to 1. So if I said 1 mole of sodium phosphate was dissolved, you would end up with 1 mole of phosphate. So the phosphate part is easy. Phosphate literally equal to 1.023 times 10 to the minus 3 molar. But the sodium has a 3. So in water, you end up with 3 sodium ions per sodium phosphate. So if you want to find sodium, you've got to multiply the sodium phosphate concentration by 3. So 1.023 times 10 to the minus 3 times 3, you end up with 3.069 times 10 to the minus 3 moles per liter. That's the concentration of the sodium ion in this solution. It's 3 times as much as the phosphate. 12 milliliters of 0.125 molar barium chloride is diluted with 9 milliliters of water to a total volume of 21 milliliters. What's the concentration in molarity of the new solution? Then it says what's the concentration molarity of chloride in the solution, the final solution, and then it says how many grams of barium chloride are in the final solution. Okay, there's going to be a couple different ways to solve some of these, but the first part is an example of what's called dilution. And in the chapter 4, part 2 lecture notes, I talked about an M1V1 equals M2V2 or some variation of that to do these kind of problems. And that's absolutely what I would use right here. You're taking a concentrated solution, 0.125, and you're diluting it. Like it went from 12 milliliters to 21 milliliters. And the goal of this first part is to find M2. What's the concentration of the new diluted solution? And the answer should be less than 0.125 molar because we've added some water to it. So for this problem, M1V1 equals M2V2. M1, 0.125. M2, 12 milliliters. You don't have to change milliliters to liters. M2 is what we're solving for, and V2, the new total volume, 21 milliliters. So if you do this, you can see then that M2 equals M1 times V1 divided by V2. I use liters. You don't have to use milliliters. You can use just milliliters. Same answer. Anyway, if you got 0.0714 molar barium chloride, you are good to go. So again, I would use in this one M1V1 equals M2V2, or C1V1 equals C2V2, or MIVI equals MFVF. They're all the same thing. The initial molarity times the initial volume equals the final molarity times the final volume, and you're solving for the final molarity. The second part says what's the concentration, the molarity, of chloride in the final solution. So we had 0.0714 barium chloride, and like on the last problem with the sodium phosphate, chloride is going to have a different, there's more chloride, if you will, in solution than there is barium. There's 2 Cl's for every barium chloride that goes in. So the concentration of the chloride is going to be twice the concentration of the barium chloride. And you can write it out like an equation like this. This is the initial concentration. 1 mole barium chloride has 2 moles of chloride. And remember, this M right here, it is moles per liter. It's technically moles of barium chloride. And so you can see how if moles of barium chloride are on the top, then this part will cancel. We'll end up with moles of chloride per liter, which is still molarity. Molarity of chloride, 0.143 molar chloride. Very cool. 3 sig figs, all that kind of stuff. Now it says how many grams of barium chloride are in the final solution. And this is where there's going to be more than one way to do it. In this example, what I did is I took the diluted solution, 0.0714 moles per liter, and I first got rid of the volume. And at 21 milliliters, that would be 0.0210 liters. I kind of have to use liters here because I want to get moles of barium chloride by itself. I'm doing that because a mole of barium chloride off the periodic table, 208.23 grams. So this answer comes out to be 0.312 grams barium chloride. Now, you will get the exact same answer if you take, intentionally or unintentionally, the initial volume and concentration. So if you took 0.125 molar barium chloride, and you multiplied it by the volume in liters, 0.0120 liters, and then multiplied it by 208.23, you should end up with 0.312 grams as well. So either way is fine. Pick your poison. As long as we all get to the final answer, we are good to go. In this problem, we're going to learn how to create a balanced chemical reaction. And the punchline of this is that all of the atoms on the reactant left side must equal the atoms on the right or product side. So as an example on A there, you can probably see that although you have 1 chromium atom on both sides, Cl2 has only 2 chlorine atoms, while CrCl3, chromium 3 chloride, has 3 chlorines. So this reaction is not balanced for atoms. The atoms on the reactant left side are not equal to the atoms on the product side. Now, one thing you can do on these, which is always okay to do, and I do it myself, is I create like a ledger. And what I do on this is I put a line down the middle, and then I'll list the types of atoms which are on both sides. So in this reaction, there's only chromium and chlorine. It's pretty chill. And then what I'll do is I'll literally count the atoms on both sides. So on the left side, there's 1 chromium atom, and Cl2 on the left side would have 2 Cl atoms. Now, if this is a balanced reaction, the right-hand side should have the same numbers as the left side. But as we talked about, they're not the same. We have 1 chromium, and CrCl3 has 3 atoms. So this reaction is certainly not balanced. Now, it's tempting to say rewrite the little Cl2 as Cl3 because woohoo, that would be equal atoms on both sides. But you don't touch the subscripts, all right? Don't touch the 3 on CrCl3. Don't touch the 2 in Cl2. That's how these molecules come together. But what you can do is you can change the stoichiometric coefficients that go in front of the molecules. Those are the big numbers that you can see. So as an example, 2 and 3, the numbers by the chlorines on the left and the right-hand side, if you multiply them together, 2 times 3 is 6. That's the common denominator of these numbers. And if you take 6, the common denominator, and divide it by the 2 of Cl2, you'll get a 3. So one thing I would do is I would put a big 3 in front of Cl2. Now that changes my 2 chlorines then to 3 times 2, 6. No problem. Let's do the same thing on the product side. 6, the common denominator, divided by 3 in CrCl3 would give 2 CrCl3s. Now 2 times 3, that changes the chlorines to 6, but alas, now you can see that we've messed with the chromiums. So now chromium's not in balance. No problem. We can put a big number in front of chromium, and it will only change the chromium, which is kind of cool. So let's write a big 2 right there, and that will then let everything be balanced. And now you can see there's 2 chromiums on the left and the right side, and 6 chlorines on the left and the right side, which is pretty cool. So the fancy version of what I just wrote there, 2 chromiums plus 3 chlorines gives you 2 CrCl3s. And that's an example of a balanced reaction. Now notice that those big numbers, those coefficients, do not balance. Like the 2 plus 3 on the left does not equal 2 on the right. Those numbers don't have to balance, but it's the number of atoms that have to balance, which is really cool. Now along the way in this problem set, we're going to get big time into the 7 diatomics. Have no fear of ice clear brew, or whatever statement you want to use, but those 7 will always appear as 2s, as pairs, all right? And notice in the problems here, for example, chromium is just a single atom. It's by itself, so it's not Cr2. Iron is just Fe. It's not Fe2 because it's not on that list. But if you have, for example, oxygen, or if you have hydrogen, those will be diatomics. That's going to be pretty important in this section. Keep those in mind as we go through these problems. The next one is iron plus water making Fe3O4 plus H2. Now, Fe3O4 to me looks the scariest, and I know that's a dumb word to use, but it seems kind of appropriate somehow. Fe3O4 has the most atoms. Maybe that's why I'm scared of it. I don't know, but anyway, for some reason that works for me. So I'm going to try and get that thing all balanced out. Now, notice that iron is by itself and H2 hydrogen is by itself. So I'll try to do those 2 last. So let's tackle the oxygen and the Fe3O4. If we put a 4 in front of the water, that gives us 4 oxygen, which is good because Fe3O4 has 4 oxygens. By doing that, then we have 4 times 2, 8 hydrogens. And as we saw, hydrogen comes in pairs of 2, so I guess we better put a 4 right there. And then the last thing to balance is just iron. It looks like if you put a 3 right there, we should be good to go. So all of this looks really good. Let's see what the final answer is going to be. Lo and behold, everything is right. 3 irons plus 4 waters makes Fe3O4 plus 4H2. Everything is balanced. I don't believe you, Dr. Russell. Oh, good question, random student in the back of the room who I can't make out. Stupid joke. Anyway, if you don't feel that maybe this is balanced, all right, or you don't trust me, oh, heaven forbid. Anyway, for whatever reason, you're always welcome to balance the reaction. Again, just make sure it's balanced. So this one is weird. Let's balance it, all right? So what I'm going to do here is I'm going to do this register thing in the middle. I'm going to put, for this one, iron. I'm going to put hydrogen and oxygen. So in this balanced reaction now, we have 3 irons, we have 4 times 2, 8 hydrogens, and 4 times 1, 4 oxygens. If this is a balanced reaction, the product side will have the same number of atoms. So let's check this out. Fe3O4 has 3 irons. Fe3O4 has 4 oxygens, and 4 times 2, 8 hydrogens. Check, check, check. Atoms the same on both sides. My friends, this is a balanced reaction. Pretty cool. Always feel like you can do that. You never can't do it. All right. And honestly, I recommend doing it just to make sure that all is well. For C, SF4 plus water makes SO2 plus HF. Nothing is by itself. We don't have any elements by itself. So this one's a little bit crazier. So there's a couple different ways to tackle this. What I'm going to do is I'm going to first look at the oxygen, and I recommend just kind of playing with these until you get it right. So notice it's SO2 on the right and H2O, 1 oxygen on the left. So the first thing I might try here is to put a 2 right there. That'll make the oxygens balanced at the least, which is pretty cool. And now by doing that, I have 2 times 2, 4 hydrogens, and HF only has 1 hydrogen. I'll start by putting a 4 right there. And if you look then, we have 4 fluorines on the left, 4 fluorines on the right, 4 hydrogens on the right, 2 times 2, 4 hydrogens on the left. 2 oxygens on the left, 2 oxygens on the right. I believe everything's balanced, and sure enough it is. All right, and again, you don't believe me, that's totally fine. You're welcome to go back and stuff and figure this all out. It's not a problem. You can check yourself at any time and make sure that you're good to go. It's not a problem at all. The next one is a little bit tricky though, and here's why it's tricky. Oxygen appears in both products on the product side, and oxygen is only on one reactant. So if we adjust just one of them, there could be a problem adjusting the other one as well. And I'll show you what I mean by that. Now, oxygen's by itself, so let's leave oxygen alone until the very last minute here and see if we can make something happen. Okay, so on this one, I see that the hydrogens, we have 3 hydrogens in NH3 and only 2 hydrogens in water. And 3 times 2 gives 6, the common denominator. So I think on this one, what I would do is I would start by putting a 2 in front of the NH3, and because 2 times 3 is 6 hydrogens, and I would put a 3 by the water. 3 times 2 would be 6 hydrogens. That would give you all the stuff you need. However, by doing this, notice that now we have 2 nitrogens on the reactant side, and we currently only have 1 nitrogen in NO on the product side. So one thing I'm going to have to do is put a 2 right there just to make sure that the nitrogens are balanced. So the only thing we have left now, I believe, to balance is oxygen. But again, as always, feel free to make one of these kind of ledger things and let's see what's going on. For this reaction, we have nitrogen, we have hydrogen, we have oxygen. On the reactant side right now, there's 2 times N, 2 nitrogens, 2 times 3, 6 hydrogens, and right now we have just 2 oxygens from O2. Now on the product side, we have 2 nitrogens from NO, 2 times 1, 2 oxygens from NO. The water would have 3 times 2, 6 hydrogens, and water also has 3 times 1, 3 oxygens. Notice how I write oxygen as 2 plus 3. That helps me remember that there's oxygen in 2 different places. However, now we can see what the issue is. You've got 2 nitrogens on both sides and 6 hydrogens on both sides, so we're good to go there. But we have 2 oxygens on the reactant side and 5 oxygens on the product side. An odd number can be found on the right and an even number on the left. And this is the joy of the diatomics, all right? Because oxygen only comes in pairs, in 2s. We want to have, though, 5 oxygens, which is how many we need on the right-hand side to balance. Now, mathematically, what would be really cool here is if we could write 5 halves in front of the O2, because 5 halves oxygens times 2 oxygens per O2, you can see how the 2's cancel, we would have a 5. So if we could just write 5 halves right here, this would be a balanced reaction. Woohoo! However, chemists hate fractions. There's only going to be one time that you're allowed to use fractions in chemistry, and this is not the time, unfortunately. However, if 5 halves would balance it, what you can do then is multiply everything through by 2, all right? Because that will get rid of the fractions, and then everything will be balanced. So let's multiply the 2 there by 2 to get 4. Let's multiply 5 halves by 2 to get 5. The 2 of NO times 2 would be 4, and the 3 times 2 would be 6. So 4, 5, 4, 6 should give you a balanced reaction. And sure enough, that is the answer to this problem. 4 NH3s, 4 ammonias plus 5 oxygens makes 4 NO plus 6 waters. So hopefully these will give you an idea of how these work out. Again, you want to try and leave the simplest piece until the end, so like chromium or iron or an element by the end, which is cool. It's kind of nice and stuff just to sometimes play with things and see what's going on. And again, you can always check yourself at the end to see how you're doing, see if the problem is balanced or not, stuff like that. You should be a master of this in no time. Decide which of the following is water soluble. If it is soluble, tell what ions are produced. Describe them as strong electrolyte, weak electrolyte, or non-electrolyte when placed in water. This is a problem now where the solubility guide is going to be handy. I talked about it at the beginning of this video, video, I would definitely recommend you get it out. But I'll talk you through how this all works as well. For the first one, nickel 2 chloride, and the question is, does it dissolve in water? The chloride is going to be the key, and chloride, bromide, and iodide, if you look on that solubility guide, are usually water soluble. So usually you would write AQ next to them. You don't write AQ though if chloride, bromide, and iodide are connected to silver, mercury, or lead. Nickel is not one of those though, so that means nickel 2 chloride is water soluble, and you would write an AQ next to it. Now, for right now, if something is water soluble, that usually means that it's going to be a strong electrolyte. So for the first one then, I would definitely say that. Oh, here's the solubility table. I make these things and I forget about them, so sorry, I'm a spacey chemist, spacey instructor, sorry about that. But anyway, here's what I was talking about. Chloride, bromide, and iodide are usually soluble. An exception would be if one of those were with silver, mercury, lead. Nickel's not one of them. Nickel 2 chloride is definitely water soluble. All right. So in this problem, you would write NiCl2AQ. It's very water soluble. It's going to have a strong electrolyte. The next one, CrNO33. Nitrate, NO3-1, is above the area with chloride. Nitrate is always water soluble, and there's no exceptions. So anytime you see nitrate or sodium or potassium with something else, always going to be water soluble. So definitely by CrNO33, you would write AQ next to it. It's soluble. It's going to break up into chromium 3+ and nitrate ions, and it is definitely a strong electrolyte. The next one, ethanol. Ethanol is a compound with carbon, hydrogen, and oxygen. It's a covalent bond. It is not an ionic bond, so the solubility guide doesn't help that much. Ethanol, which is drinking alcohol, is used by lots of people when they want to have a drink. And just say no, kids, especially if you're under 21 in the United States, 19 in Canada. However, ethanol does dissolve well in water. So like vodka, for example, is essentially ethanol with water, different concentrations, blah, blah, blah. The non-metal compounds, the covalent bonds, are not going to make ions though. So ethanol, we would say, is water soluble. All right, ethanol, drinking alcohol, dissolves really well in water, but because it has only CH and O, it doesn't have like metals and non-metals with it. There's no positive, negative ions. It's a non-electrolyte. It does not conduct electricity. There are several examples of covalent compounds that do dissolve in water, but they're not electrolytic. Sugar is another example of this. Sugar dissolves in water. It doesn't make any ions. Acetone would be another one used for like fingernail polish remover and stuff like that. So you only have ions and electrolytes if you have individual ions, and we don't have that here. Ammonia is NH3, and ammonia, if it was just a covalent bond, we would expect it to maybe be soluble but not be electrolytic. But ammonia has another feature. Ammonia, as we're going to see, is a weak base, and weak bases are actually a little bit electrolytic. They will conduct electricity because they end up making, in ammonia's case, some NH4+ and OH-. So I would say that ammonia is soluble, but it's a weak electrolyte. Weak bases and weak acids don't conduct electricity super well, and so that's why they're considered weak electrolyte. There are some ions, maybe 1 in every 10,000 of the ammonias will break up. Most of them stay the same, so that's why it's kind of limited. Finally, the last one, barium sulfate. If you look on the solubility table with sulfate, sulfate is usually water soluble, but barium, when it's with barium, that's an exception. Barium sulfate is decidedly insoluble. We saw that earlier with the saccharin problem we talked about. So barium sulfate is insoluble. It does not make ions. If it doesn't dissolve, that means it doesn't have positives and negatives. And if it doesn't have positives and and negatives, it is a non-electrolyte. But it's a different reason than ethanol. Ethanol was a non-electrolyte because you don't have positives and negatives when it's in water, when it dissolves in water. Barium sulfite is a non-electrolyte because it doesn't dissolve in water. Different reasons there for what's going on. Ethanol was covalent. That's why it didn't make ions. Barium sulfate just doesn't dissolve because it likes being with itself. In this question, we want to predict the products of each reaction, balance the completed equation, then write the net ionic equation, and identify any spectator ions. Oh boy. Okay, how these reactions work, and by the way, this is going to be the focus of the net ionic reactions lab coming up. But anyway, how they work is you want to have the similar species trade places with each other. So on A, lead and potassium are both metals. And what's going to happen in these kind of reactions is they're going to switch places. So the lead will start dancing with bromide, and the potassium will start dancing with nitrate, NO3. Now, on these kind of reactions, the charges do not change. So lead is a positive 2 on the reactant side, nitrate is negative 1, and there's 2 of them, so that's a lead 2 plus. Lead is going to be positive 2 on the other side. And why that's important is because bromide is negative 1. It's group 7, 7 minus 8 minus 1, etc., and it only has one positive potassium with it. So to make a neutral compound with lead 2 plus and Br minus, you would write PbBr2. Positive 2 lead with 2 negative 1 bromides will make that a neutral compound. Now we only have one Br right now. We'll take care of that in a little bit, but it's important to think about the raw charges on the individual pieces and then figure out what kind of neutral combination can come between them. Now we're going to do the same thing here with potassium and nitrate. Potassium is positive 1 and nitrate is negative 1. So we want to write here KNO3. And when you're learning this, it's tempting to write K parentheses NO3 parentheses 2, but that's not correct. The charges aren't going to match. K is plus 1, NO3 is minus 1 if you remember from nitrate, so KNO3 is the neutral compound that comes from there. So this reaction is not balanced by any means yet, but we'll do that now in a second. We'll add some appropriate coefficients. So you can see, for example, there was 2 NO3s and I only used one of them. So that means we're going to write a 2 right there in front of KNO3. And because we needed 2 bromides to balance the lead, but there's only one KBr, one bromide, we're going to add a 2 right there. So this is an example of a balanced reaction. And we just used the exchange process or double displacement process to figure it out. The metals just swapped places with each other. They started dancing with the other nonmetals on the other side. We had to figure out the raw charges first and then go from there. Pretty chill. To finish this problem off, we're going to need to know the states of matter, because the states of matter will help us when we get to the net ionic part and spectator ions. Now, it said on the left that PbNO3 is aqueous and KBr is aqueous. We don't need to change that. Anything with a nitrate and anything with a K plus is always going to be aqueous. So you can see there that there's an aqueous next to the KNO3, no problem. But PbBr2, bromide, chloride, and iodide are usually aqueous unless they're with silver plus, mercury 2 plus, and lead 2 plus. And lead 2 plus is what we have here. This is lead 2 plus with 2 Br minuses making a compound. So PbBr2 is insoluble. All right, it's going to make a solid, and that's good to go. So this reaction isn't just a complete balanced reaction. It actually shows the states of matter, and that's going to be important for us here in a little bit. To find the net ionic equation, remember that anything that's aqueous, and 3 of our 4 species here are aqueous, anything that's aqueous doesn't actually exist in its molecular form. It dissociates into the ions. So for example, we could write this as Pb2 plus and 2 NO3 minuses. It doesn't exist as PbNO3 in water. It actually exists as Pb2 plus and NO3 minuses. And you could write AQ next to them, but I probably won't do it on this problem. KBr, we're going to do the same thing. It's going to break up into 2 K 2K plus and 2Br minus. But here's the important part. Solids, liquids, and gases, don't break them up. They stay together. So we're not going to break up PbBr2 since it's a solid. We're just going to rewrite PbBr2 solid. Again, don't break up solids, liquids, and gases. Now, KNO3, though, is aqueous, so let's write 2K plus and 2NO3 minus, because the aqueous things break up. Now, mathematically, if you look at this equation, notice that there's two nitrates, one on each side of the reaction. One's a reactant and one's a product. Nitrate is an example of a spectator ion. It's not participating in the chemistry of this reaction. So if you can cancel something on both sides, that's going to be a spectator ion. Nitrate is a spectator. And you can probably see that there's a second spectator. 2K plus are on both sides of the reaction as well. So in this reaction, 2K plus and 2NO3 minus, or potassium ions and nitrate ions, those are the spectators. They're not participating in the chemistry. So the net ionic equation is basically what's left. It's going to be lead-2 plus aqueous plus 2Br minus aqueous going to PbBr2 solid. Again, don't break up solids, liquids, and gases. Lead-2 plus aqueous is different than PbBr2, just like 2Br minus is different than PbBr2. So this is how this stuff works. So again, what we did here is we first did the exchange reaction. Lead and potassium swap places to make PbBr2 and KNO3. We balanced the reaction. We used the solubility guide to determine that PbBr2 is a solid, it's a precipitate, while KNO3 was aqueous. Then we broke apart all the aqueous parts. That means Pb and NO3 minus separated, the K plus and Br minus separated. On the product side, though, don't break up solids, liquids, and gases, so PbBr2 stays together, while K plus and NO3 minus separate. Anything that's on both sides is a spectator, so potassium and nitrate are both spectator ions here, and the net ionic reaction, Pb2 plus 2Br minus, makes PbBr2. Let's look at a better version than your instructor's version here in just a second. There's a much nicer version than your instructor's handwriting. The spectators, again, are K plus and NO3 minus. These are the parts that were on both sides of the reaction. The action of the reaction, as I call it, is the net ionic equation. It's lead and bromide coming together to make this PbBr2. The K plus and the NO3 minus were just kind of chilling out. They weren't doing anything. And why this is important to chemists, let's say that you really wanted to see PbBr2 made in lab. It's a pretty cool yellow solid, by the way. Well, anyway, we come to lab, and sure enough, we have lead-2 nitrate, PbNO3-2, but oh man, we ran out in the stockroom of KBr. Darn it. Well, instead of going home with sad faces, if we look around, we found some NABr, all right? And NABr has bromide, one of the active ingredients. Na will be a spectator, just like K+. So you can substitute NABr in. If you don't have any KBr, you'll see the same reaction, all right? So that's where the power of a spectator comes in. If we had lithium bromide, that would work too. Ammonium bromide would be okay. We just need to substitute one spectator for another, and a lot of times you'll have one thing in the lab but not the other. So knowing about spectator ions can be pretty cool. In B up there, it's the same kind of thing. Magnesium and H+ will swap places with each other. The magnesium will be on the other side to make MgCl2. Magnesium is +2 on the left, chloride's -1, that's why there's two of them. And then H starts dancing with OH. Now, HOH is fine if you want to write it that way, but of course, most people will write that H2O, water, all right? And water is the one liquid that you need to know. So make sure that you know that water is normally a liquid unless you're told otherwise. To balance this thing out, we're going to need 2 HCl because 2 chlorides are needed to make MgCl2. And that means 2 H's and 2 OH's of the magnesium hydroxide will make 2 waters. So this reaction then is going to be MgOH2 solid plus 2 HCl aqueous makes MgCl2, which by the way is aqueous. It's not silver, lead, or mercury, as I talked about earlier, plus 2 waters. That's the balanced reaction. Here's a nicer version than what I wrote right there, but you can see the idea. MgOH2 plus 2 HCl makes MgCl2 aqueous plus 2 waters. Now, to get to the net ionic equation, remember once again, don't break up solids or liquids. And we have both MgOH2 and water here. Don't break them up. But we will break up the 2 HCl's into 2 H plus and 2 Cl minus. We will break up the MgCl2 into Mg2 plus and 2 Cl minus. So hopefully you can see from my sad handwriting there that 2 Cl minus is going to be an ion on both sides. Again, don't break up the solid MgOH2, don't break up the liquid water, but we can break up anything that's aqueous. And sure enough, chloride is in both of those. Chloride here is going to be a spectator. So if you rewrite all of this, it's MgOH2 solid plus 2H plus aqueous, and that goes to Mg2 plus aqueous plus 2 waters. And because we canceled the chloride out, chloride is a spectator. Chloride is the spectator ion in this reaction. Cool. For the last one then, we have calcium, which is a metal, and H+, which is also positive, so it's kind of like a metal, and they're going to shift places. So calcium's positive 2, nitrate's -1. That's going to make CaNO3 2, and anything with a nitrate is aqueous. Don't have to worry about that. But more interestingly here, carbonate, CO3 is -2 and H is +1. When you combine those together, H2CO3. And by the way, we're going to need 2HNO3 to make that happen. Now, H2CO3 is a little weird at first, unless you remember that it's an unstable acid. It's called carbonic acid. And carbonic acid breaks down to H2O and CO2 gas. So it breaks down to a liquid and gas. So if you see H2CO3 form, just realize it doesn't stay together. And honestly, it's better to write H2O plus CO2. You can have a little arrow there kind of going off showing it's the side, or you can just not include it because the hip chemist should know that it makes H2O and CO2, not H2CO3. The overall balance reaction here, 2HNO3AQ plus CaCO3 solid makes CaNO32AQ plus H2O liquid plus CO2 gas. Notice that there's no mention of H2CO3. That's implied that that naturally breaks down into that, so that's why that's happening. Like before, break anything down that's AQ, but leave the solids, liquids, and gases alone. So don't touch CaCO3, don't touch the H2O, don't touch the water. So HNO3 would be 2H plus and 2NO3 minus. Calcium nitrate is also aqueous. That would break up into calcium ions and 2 nitrate ions. And lo and behold, 2 nitrate ions are on both sides. So nitrate here is going to be the spectator. It cancels out. So at the end of the day, you're going to have 2H plus aqueous from the nitric acid plus calcium carbonate, a solid. Don't break that up. That goes to calcium 2 plus aqueous. That gets broken up, but leave the calcium in, plus water plus CO2. Don't break up the liquids and gases. Nitrate here is going to be a spectator. Here's a fancier version than what I wrote earlier, but it's the same idea. 2H plus remained from the HNO3. The solid calcium carbonate stays as it is. Calcium 2 plus aqueous comes down from the aqueous nitrate. Water and CO2 survive, and the spectator here is nitrate. So what you've done in this problem is pretty powerful. First of all, you've seen some real common patterns of reaction. These are called double displacement or exchange reactions. The like pieces will trade places with each other, and you end up then with new products. And knowing about solubility, you can make predictions as if to their solids or waters formed and stuff like that. That's pretty cool. We also learned then how to do a net ionic reaction. That's the action of the reaction, the exciting part. So making PbBr2 and A is the exciting part, all right? The KNO3 is boring. K plus and NO3 minus just kind of float around and don't do anything. They're not very exciting at all. And lastly, I didn't mention that, but what we're going to do is we're going to start classifying these as types of reaction. The first one, A there, it makes a solid. That's going to be a precipitate reaction, which is kind of cool. The second one, you have HCl, an acid. MgOH2 is a base. Metal hydroxides are base. OH minus is hydroxide. This is an acid-base reaction, and water is being made, as well as a salt, which is MgCl2 in this case. Pretty cool. And the last one, because CO2 gas was made, this is a gas-forming reaction. The unstable carbonic acid was made, but we didn't even include it because it automatically basically breaks down to water plus CO2. Pretty exciting. If you have an acid with a metal carbonate, which is what calcium carbonate is, that's going to create a gas-forming experience, the H2O and the CO2. So pretty exciting problem with a lot of potential when it comes to being a chemist. Determine the oxidation number of each element in the following ions or compounds. Oxidation numbers are really helpful when it comes to determining if something has been reduced or if something's been oxidized. And to know how oxidation works, you can see this stuff a little bit better. There are some basic rules, and we talked about them a little bit in the Chapter 4 Part 2 notes, how they work. But the important part here I'm going to sum up and I'm going to use is that the sum of all the oxidation numbers in a formula is going to equal the charge on the compound, if any. So we'll deal with that here in a little bit, and I'll show you. Now, the first one, O2 gas, that's elemental oxygen. And all elements from O2, all the have no fear of ice clear brew, as well as, say, pure magnesium and krypton and mercury, etc., all of those will be zero. All elements in their standard states are equal to zero. Now, oxygen, O2, can actually be a liquid, for example. That would be a place where it wouldn't have necessarily an oxidation number of zero. You can also have things like ozone, which is a non-standard state of oxygen. That would also have some unusual oxidation numbers, but most of the time, O2 by itself going to be zero. Now, oxygen in a compound is different. Oxygen in a compound almost always is going to be -2. So on B, the oxygen there in CuO, I would say that's oxygen is -2. The sum of all oxidation numbers equals the charge of the compound, if any. CuO does not have a charge. So let's say you didn't know what the copper was. You could literally think about it as the oxidation number of the copper plus -2 for the oxygen, because oxygen's almost always -2, equals 0. CuO is a neutral compound. So the only way you can make that equation work, of course, is if copper has an oxidation number of +2. So in this molecule, copper is +2, oxygen is -2, and oxygen's almost always -2. It's not -2 when it's with fluorine. It's not -2 when it's with a peroxide, which is weird, but most of the time in a compound, oxygen will be -2, and the copper has to be +2 if the sum of the oxidation numbers equals 0, the charge on the compound. The next one is a uranium oxide compound, and you can see there's a U and an O, but there's also a charge of +2. So while on the last one, copper's oxidation number plus oxygen's oxidation number equals 0 because it was neutral, here the uranium's oxidation number plus the oxygen's oxidation number equals +2. It equals the charge on the compound, if any, and this one has a charge. Now, oxygen, we saw again, -2 almost all the time. So uranium plus -2 equals +2. And the only way you can make that equation work is if that's a uranium +4. So this is a uranium +4, oxygen -2. And again, note how 4 minus 2 equals the charge on this compound, +2. That's what it means. D, Oxygen, like we've talked about already, almost always -2. Hydrogen, almost always +1. There are rare things called hydrides. Hydrides are a metal hydrogen compound. This is definitely not a metal hydrogen compound, so like most of the time, hydrogen will be +1. Now, the 2 +1 hydrogens plus arsenic, and arsenic can be all over the place, plus 4 -2 oxygens, all of that together equals -1. So it's like 2 times +1 plus X, we don't know arsenic, plus 4 times -2 equals -1. So again, one unknown, basically X, the charge on the arsenic, everything else is known. You should see that's a +5. And again, hydrogen almost always +1, oxygen almost always -2. But oxygen is not always -2. When oxygen is with fluorine, like on E, oxygen will take a positive charge. Fluorine in a compound is always -1. So if there are 2 -1 fluorines, and that -2 plus oxygen is going to equal 0, because OF2 is neutral, that oxygen there is going to be a +2. So again, oxygen will not be equal to -2 if it's with fluorine or a peroxide, which are both rare, but I wanted to show you one here just to shake it up, I guess. Fluorine is always -1 in compounds, no exceptions. And then the last one, oxygen, again, -2, and there's 4 of them, -8. You've got to have a -2 charge left over. That xenon is going to be a +6. All right, so if you've got these down, you're good to go. And again, these will help us to determine what's been oxidized and what's been reduced. Which of the following reactions are oxidation-reduction reactions? Explain your answer briefly and classify the remaining reactions. Okay, there's a couple different ways you could tackle this reaction. And one way to do it would be to go through and find the oxidation numbers of all the elements in atoms in the compounds for the different reactions. And if you don't see an oxidation number change going from reactant to product, then it's not a redox reaction. So bear with me here, and I'm going to do this kind of fast. Chlorine, almost always -1, and there's 2 of them, so cadmium, +2. Sodium, almost always +1. Sulfur here is going to be -2. Cadmium sulfide on the product side, +2 and -2 sulfide. Sodium, +1 and -1 chloride. If you look at the numbers, all right, the cadmium's +2 on the left and the cadmium's +2 on the right. Same thing for sulfur. Sulfur is -2, sodium's +1, and chloride is -1. So what that means is that no atoms changed oxidation number going from reactant to product. And that means A is not a redox reaction. If you remember from the types of reaction, cadmium and sodium are trading places. You're making a solid, a precipitate reaction. This is a double displacement/exchange reaction where a solid is made, so we call it precipitation. So, A is not a redox reaction. And I'm going to be honest here, all of the double displacement reactions we looked at are not redox reactions. So this was a precipitation reaction. And in the future, you can just say, hey, that's a precipitation reaction. That's not a redox reaction. And you would be absolutely right. Acid-base reactions are not redox, and also gas-forming reactions are not redox. Now, on B, let's do the same oxidation number. Calcium and oxygen here are pure elements, so their oxidation numbers are 0. But in calcium oxide on the right, this is a compound. Oxygen, -2 almost all the time in compounds. Calcium would be +2. Now you're seeing changes to oxidation number. Calcium is going from 0 to +2. Calcium must be losing electrons, because the only way it can go from a 0 on the left to a positive 2 on the right is if it loses 2 electrons. And loses 2 electrons, loses electrons means oxidized. Calcium has been oxidized. But if something's being oxidized, you have to have something being reduced. The oxygens are going from 0 to -2. Oxygens are gaining electrons. Oxygens are gaining electrons. They're being reduced. So B is an oxidation reduction reaction. And the ultimate way to do that is to see that calcium has changed its oxidation number. It's become more positive. It's lost electrons. Oxygen has become more negative because it's gaining electrons. Finally, a quick way to do this, if you see an element disappearing into a compound or a compound creating for somehow an element, those will almost always be redox reaction. And in B, we have calcium, the element, the elemental neutral version, plus oxygen, neutral oxygen, making a compound. So B screams, basically, redox reaction. You can always go back to the redox numbers, but it's also good to do that. So on C, we could go through and do the redox numbers again, the oxidation numbers again, and you will see that this is a oxidation reduction reaction. But also notice that we've got elemental oxygen as a reactant, and it's quote-unquote disappearing into the product FeOH3. This is definitely going to be a redox reaction because as elemental oxygen, that O2 is 0, and in FeOH3 on the product side, that oxygen is going to be -2. Now, the goal here is to figure out what else is happening, because if oxygen is gaining electrons, something, of course, has to be losing electrons. And if you look at this long enough, or you go through and figure out the oxidation numbers, iron plus 2 on the left is becoming iron plus 3. Each iron is losing an electron. It's being oxidized. So the oxygen is gaining electrons, being reduced. The iron is losing electrons. It's being oxidized. This is a redox reaction. Cool. The last one looks a little weird. Magnesium carbonate and 2HCl makes MgCl2 plus H2O plus CO2. But if you remember from the types of reactions, carbonic acid H2CO3 breaks down to H2O and CO2. And if it, instead of H2O and CO2, you wrote H2CO3, it might be easier to see that magnesium and hydrogen are trading places. Hydrogens start dancing with carbonate to make what's at first carbonic acid, which breaks down to CO2 and water, and magnesium chloride is the other product. So this is a double displacement reaction. This is not a redox reaction. It's not a precipitation reaction like we saw earlier. And although we do have an acid, this isn't an acid-base reaction. The presence of CO2 as a product here from the carbonic acid makes this a gas-forming reaction. So it's not redox. If you go through and find the oxidation numbers of all of those elements, they're all the same left and right. It's a gas-forming reaction. CO2 has been made. So you can see how knowledge of these reactions can be kind of helpful. Okay, so that's it for problem set number 6. I appreciate you being here. If you have questions on this material, definitely check out both the study guide and the concept guide for both Chapter 6 and Chapter 7, Part 1. Those are both in your companion, and they're also online. There's also the online-only chapter guides, which you can check out for more information as well. I really appreciate you being here. I know your time is limited, but I appreciate you studying this and trying to figure out what's going on. If you have questions on anything, let me know. Talk to the LSC/Avid Center. Thanks for spending your time with me. Good luck with your studying, and have a wonderful day.